5.6b is where we're on, but are there questions? No? Okay. All right then, page 91. In an acid-base titration, so here's a picture of an acid-base titration, and we have a burette containing NaOH. And it has a known concentration. What do we call it if it has a known concentration? Do you guys remember? It is the titrant, but it's also called the standard. Also called the titrant. But definitely when you know the concentration, it's known as the standard. And in fact, one of the things you'll be doing in our post-lab titration, post-Christmas lab titration is standardizing some sodium hydroxide solution, because it's really actually very difficult to make sodium hydroxide to an exact concentration, because the solid actually absorbs carbon dioxide and water from the atmosphere. So like when you weigh out the mass, you don't actually know how much NaOH you're getting. You're getting like other stuff in there too. So yes. Okay. So you can either use a indicator to change at the, what do we call that point? When the acid equals the base. That's the transition point, is the point where the indicator changes color. What do we call it when the acid totally neutralizes the base? That's the equivalence point. So that's when the acid is completely neutralized by the base. Now, alternately, or maybe even at the same time, so and or, you can use a pH meter to monitor the progress of the reaction. And what do you think will happen? We have a little question here. This is from BLB, the big black textbook. Go figure. In which direction do you expect the pH to change as NaOH is added to the HCl solution? Tell your partner, what do you think? Will the pH go up or will the pH go down? pH will go up. Why? Because we're adding base, right? We're adding NaOH. So we're starting with acid down, and in this case, it's a beaker, because one thing that you can do is with a pH meter, you need space to put in the little probe. And you know how you swirl the flask? You can actually have it stir automatically. You get like a little magnetic stirring bar and you put it on a stir plate, and then the little magnet goes automatically and stirs for you. How nice is that? Okay. All right, a review of terms. Here's our titration setup. What else is the titrant known as? That is our standard solution. And is that the known or the unknown? That is our known. Okay. How about, oh my God, let's get rid of the titrand, because I don't like that. That's too confusing. There's too many. Titrant, titrand, no, just get rid of that. What else could we call the analyte? We could call it the unknown. It is also often known as the sample. You're going to sample something and you're going to analyze it. Yes? So you can either call it the sample or the analyte, because you sample a solution and then you analyze it. Okay, and we have, of course, our conical flask. What's the other name for a conical flask? Erlenmeyer flask. What's that big long tube called? Burette. There's two spellings for burette. E-T or E-T-T-E. It does not matter. And usually also in here goes a indicator. But if you're doing if you're monitoring with pH, you don't have to have an indicator. Okay? I'm going to get rid of the word titrant. That irritates me. Sample. There we go. Okay. What do we call the point in the titration where the amount of titrant added is just enough to completely neutralize the analyte? That is called the equivalence point. Yes. That is our equivalence point. There's another kind of point, and that is called the end point. What is the difference? What is an end point? It's where the indicator changes color. Huh? Isn't what with who? Yeah, where the stoichiometry is perfectly fulfilled. Yes. So endpoint is the point where an indicator changes color in a titration. That's different from the transition point, which is just the pH at which an indicator changes color. Okay? This is the volume and pH. Where an indicator changes color. So it is a point on a graph where you're plotting pH versus volume. So it's got two coordinates, okay? It's a point on a graph. And actually, the equivalence point can also be a point on a graph. It doesn't have to be. Have we done any graphing so far? Have we done stuff with equivalence points? Yeah. Okay, so it doesn't have to be, but it can also be a point on a graph. And that's going to be a graph of pH and volume. This will all make more sense when I show you the diagrams. Okay, we know what an indicator is. I don't think we need to talk about that. What is a titration curve? This is the graph of pH versus volume. So it's the pH of the analyte solution, the sample, versus the volume of titrant slash standard. And you always get this kind of S-shaped curve. Does anyone know the name for a graph that is S-shaped? Sorry, yes? It is sigmoidal. My grade 9s all like had a fit when we had a sigmoidal graph. Like, sigma! Good God. And they don't laugh at any of my jokes. Like when I make a joke, not at all, not even a little bit. Anyway, that's okay. So when we titrate a strong acid with a strong base, so suppose our analyte is hydrochloric acid, that is our unknown, HCl, and our titrant is sodium hydroxide, NaOH, so our known is NaOH. So who is going to be in the flask and who is going to be in the burette? NaOH is going to be in the burette, NaHCl will be in the flask. Okay, and if we start plotting the pH, we will get a titration curve that like we will see on the next page. Here we go. Woo, there we are. Did I give a concentration here? No, I did not. Oh, that's okay. I know. It's all good. So it pretty much looks like a graph, and we're going to analyze this point by point. So at point number 1, which is right here, we have no NaOH added yet. Does it make sense that the pH is low? Because all we've got is HCl, which produces H3O plus, so the pH is low. What is happening between points 1 and 2? What are we doing? We're adding NaOH. Is the pH going up a lot or a little bit? It's just a shallow slope. And then all of a sudden, at point 2 is just before complete neutralization. How much volume did it take us to get from point 1 to point 2? Let's say these are milliliters. It took 50 milliliters. Okay, so we are at point 2, we are just before complete neutralization. That's neutralization, if you were wondering. Nutrizin. Okay. What do you think has happened at point 3? We have the equivalence point. We have complete neutralization. We started, oh, look at that vertical section. We started at about pH 3-ish. What pH are we at right now? We are at pH 7. Why is the pH 7 at the equivalence point for a strong acid and a strong base? Because it's gone to completion and they've completely neutralized each other, but I can do a strong acid and a weak base and the equivalence point will not be pH 7. Why is it 7 here? What do you get as your product? We get water and we get a salt. But what do we know about that salt? That salt does not hydrolyze. What does it mean to hydrolyze? React with water to produce H3O plus or OH minus. So that's all you've got at the equivalence point. All you've got is sodium chloride, which is a non-hydrolyzable salt. So it just sits there being like, hey, pH 7, woo! And then you start adding more NaOH. And you get to 0.4. What is causing that pH to be so much higher there? That is our excess NaOH. Whoops. So down at the bottom, we have excess HCl. At the equivalence point, we have NaCl. And then up above the equivalence point, we have excess sodium hydroxide. How much volume does it take to get from just before complete neutralization to just after complete neutralization? Like point something, yes? You're like, you go drip, and you know how sometimes you go drip and it turns like, and you're like, oh, it's going to be the lightest pink possible, and then it's like dark pink, and you're like, oh. That's because that pH, when it swings from excess acid to excess base, it does a huge leap in pH in a very small amount of volume. And that's because pH is a logarithmic scale, which might mean something to some of you math people. It doesn't mean a lot to me because my brain kind of like falls off the cliff when it does too much math, but yeah. Okay, so that is our graph. And let's see what else we're going to look at here. 0.4, we had our excess OH. There we go. So after the equivalence point, yay. At the equivalence point, we just have the salt. Okay, very nice. According to this graph, What is the initial concentration of the HCl solution? And you guys get to solve that. Yep. Did you get 1 times 10 to the negative 2 molar? Yay! Okay, so now you're getting good at reading graphs. All right. What volume, and here we have another graph, what volume of NaOH would be needed to reach the equivalence point if the concentration of the added base were 0.2 molar? Now this requires us to know something first, and that requires us to go down to the bottom and read about this graph. So this is the titration of a strong acid with a strong base, and it says, why are you not letting me scroll? The pH curve for titration of 50 mils of 0.1 molar HCl. So this graph here, we are titrating 50 mils, whoops, not 5, 50, of 0.1 molar HCl with, and I think it's 0.1 molar NaOH. Yes, 0.1 molar NaOH. That's what's happening over here. What would happen to the volume of NaOH if concentration of the added base were 0.2 molar? So you're going to need to think about that a little bit. Do you think you know? Yes? It's half. Yeah, does that make sense? We've doubled the concentration. So to get the same number of moles, we would need half the volume to get there. Okay, so if we've doubled the concentration of the NaOH. Therefore, it will take half the volume to get the same number of moles. So originally, how many milliliters did it take to get to the equivalence point? 50. Yes? So now it's going to be 25. And if you want to prove to yourself that, you can say, okay, original, we had 50 milliliters of 0.2 moles per liter. And that is that 1? No, it's 10. 10 millimoles of NaOH. And then our new, we would say, how many milliliters? Oh, no, that's not our original. That's our, oh, that should be 0.1. I'm so sorry. That should be a 1 because that was our original. And that should be a 5. That should be a 1. That should be a 5. And we can say how many milliliters times 0.2 moles per liter would give us 5 millimoles. And so you take 5 divided by 0.2 and you get 25. Well, the only reason I know that is because I know the answer is 25, not because I can do that kind of math in my head. So is good? Okay, very good. So you should be able to do proportional reasoning like that. Okay? But quite frankly, I wouldn't even bother with the calculation because this is just a doubling and a halving, so you can just do it intuitively like that. Yeah? Okay, so this is just a picture of what's happening down in the flask. So at the very beginning right here, we have just H and Cl. And then, ooh, what point are we at right here, assuming our original concentration? What is that concentrate? What is that point called there? That is our half equivalence point. But it's not really very meaningful for a strong acid and a strong base. What does the half equivalence point usually tell us? Half equivalence point. Does that ring any bells? pH at the half equivalence point equals Ka, but this is pretty meaningless for a strong acid because what's the strong acid? What's the Ka for a strong acid? Yeah, okay? So this is meaningless for a strong acid. So you can see at the half equivalence point, let's just label that here. Because even though it's meaningless, you might as well start recognizing where it is, right, on the graph. At the half equivalence point, we have neutralized half of the hydrogens, because here at the beginning we had 2 hydrogens. Here we only have 1 hydrogen. And then, so this is our half equivalence point. And then we get to our equivalence point, which is pH 7. And all we have is Na plus and Cl minus. I really need to edit this so those have like actual like things on them so you can see them. That would be nice. Because you guys don't get like purple and green. You just get like gray and gray. So it would be nice if they were labeled. Did you have a question? Okay, yeah. And then over on our right, we are up here in this, we have excess NaOH. And there, you can see there is our excess NaOH. There's still some Na, there's still some Cl, and there we are. So in theory, AP does like diagrams, right? And if they were to give you one of these that was really nicely labeled, you should be able to say whether you have started the titration, whether you're at the equivalence point, whether you're after the equivalence point, or whether you're before the equivalence point. Does that make sense? If you were given like those particular particles, you should be able to maybe put them in order or something like that. Yeah? Okay, cool, cool. Now, what if we titrate a strong base with a strong acid? I know up till this point we have always put the acid in the flask and the base in the burette, but this time we have our acid in the burette and we have our base in the flask. So what should our pH start at? High, right? There's our pH, it starts high. And because this is a strong base and a strong acid, what should the equivalence point be? Equivalence point should be 7. Okay, and it basically just looks upside down of what we saw for a strong base, strong acid titrated by a strong base. So that's it. Okay, so not very much different. Starts high, finishes low, excess base. Only NaCl, excess acid, and that's basically it. Okay? So you should be able to recognize, do I have from a curve just presented to you, is it a strong acid titrated by a strong base, or is it strong base titrated by a strong acid? Okay? There we go. And now we're going to titrate a weak acid with a strong base. And before we look at this, can you predict whether the pH, what the pH at the equivalence point will be? You don't need to give me an exact number, just greater than, less than, or equal to 7. Weak acid with strong base. And this is where you can use this reasoning to just remember it. You have a strong base, you have a weak acid. Is it going to be acidic, basic, or neutral? It's going to be basic. So the pH is going to be greater than 7. Is that a good explanation? You got a strong base, you got a weak acid, so the stronger one wins. That's not a good explanation. But if you're just like, I need to have an equivalence point greater than 7, then I know it's going to be a weak acid with a strong base. Okay? Or if you're like, where is the pH going to be when I do that? You can be like, it's greater than 7. Excellent. I just know that. So we are going to have our weak acid, acetic acid, is going to be our analyte. That's our unknown. Our unk. And the titrant, our known, is going to be sodium hydroxide. It bothers me so much that sodium hydroxide breaks over the line, but that's okay. Sodium hydroxide. Our strong base, that is our known. Should we start at the same pH or a higher pH than before when we had a strong acid? We're going to start at a higher pH because this is a weak acid. So the initial pH is higher than for a strong acid. Therefore, what was I saying? A weak acid initial pH is higher than with a strong acid. So if you are presented with a curve and you are told that you have, say, 0.1 molar, or sorry, actually say you have 0.01 molar, if you're told that the concentration of the acid is 0.1 molar and you're looking at this graph, you should be able to, from the initial pH, say, this is not a strong acid. Why is that? Say, for example, it was HCl. What would your initial pH be? If our acid were HCl, what would our initial pH be based on the concentration of the acid being 0.01 molar? pH would be 2. Okay, but if the acid is weak, then the pH is going to be, pH initial is going to be greater than 2. Does that make sense? Okay, so that's one way that you can tell that this graph is a graph of a weak acid plus a strong base. Let's take a look at this graph and tell me if you can see another way you can tell that this is not a graph of a strong acid, strong base. Why is this not strong, strong? Some other feature of this graph. Sorry? It increases more from 1 to... The big one is that the equivalence point is not at pH 7, okay? And the pH is greater than 7. And that tells you what two things are you titrating. You're titrating a strong base with a weak acid. Okay, there we go. Okay. Why is the pH greater than 7 at the equivalence point? Yes? Yeah, we have a salt that's made, and we're going to have anionic hydrolysis. Okay, so the pH greater than 7. So the salt that is made will undergo anionic hydrolysis. Therefore, it produces OH minus. And if I were answering this like on a test in a written response question, I would probably take the anion and show the hydrolysis equation. Yes? Okay. So, and then does it look any different above the equivalence point? No. Why is that? What controls the pH above the equivalence point? Excess base. Does it matter what it reacted with? No. So this is the same as strong acid, strong base, because excess strong base is causing the pH there. I don't know if that makes any sense. Same as SASB, because excess SB, there's a lot of letters there. Okay, that's in a few more words. pH above the equivalence point is the same for weak acid with strong base as strong acid with strong base, because the pH is due only to the excess strong base. Same as SASB, because excess SB. Same thing. Ha! Okay. So you should be able to tell those features of the graph. There is one other feature that perhaps you might notice that's different. So here is the weak. Here is the strong. Yes? Yeah, there's a little hill at the beginning. So if you see that little hill, again, that is a giveaway that you have a weak strong. Okay? If you have no hill, so this is on page 94. No hill. Therefore, strong, strong. Page 94. pH equals 7. Therefore, strong, strong. Is good? Okay. Yes.
This question, I think that's pH equals 8. Or
Oh, at the half equivalence point, we'll get there. We'll get there. Don't worry. We got it coming. Okay, so where were we here? Okay. Okay, so here we have a little hill. This is back on page 96. 96. So we have a little hill. Therefore, weak, strong. So a weak something is being titrated by a strong something. And when we do a weak base with a strong acid, the hill's going to scoop the other way. It's going to scoop downward instead, okay? But it's still like a little hill. All right? And while we're here, let's label the half equivalence point. Why not? And if this were the case, if this were actually our half equivalence point, what would our Ka of this weak acid be? I'm going to let you think about that for a minute. Yeah, it's the pH at the half equivalence point. Well, it's the pKa is the pH at the half equivalence point. So we have here, that looks like about 4, yes? So the half equivalence point is at pH 4, and therefore the pKa is 4, and therefore the Ka is 1 times 10 to the negative 4. Okay, I mean, this is always going to be a little bit ballpark because you're reading off a graph, right? But if you were to say graph this in Excel or something like that, and I don't know if there's other graphing programs out there, but you could actually get like a very precise reading at that point. Okay? So at point number 1, there's no NaOH added yet, so the pH of the analyte is low. But is it as big as before with say a strong acid? No, because this is only partially dissociated. And that's as opposed to what we had before, where we had our strong, which is basically this all goes away and you're left with all of it dissociated. Does that make sense? So you have a bigger amount. Do you see how I use the font there? Look at the font. Small font, big font. Whoa, that's supposed to be highlight. There we go. Okay. Between points 1 and 2, as NaOH is added dropwise, H3O starts slowly getting consumed by the OH. So the analyte is still acidic due to the unreacted H3O plus. We are still continued here. Now, what kind of a solution will we have in here? Where we have, in this little section here, we have some unreacted weak acid, and we have produced some weak base, conjugate weak base. So we have some weak acid and we have some conjugate weak base. What does that make? It makes an equilibrium. It makes a buffer. So we call this the buffer region of the curve. You don't get a buffer region in strong because you can't have a equilibrium with a strong acid, right? Yes. Okay, let's go back here. When OH gets minus, it's going to react with that. What's going to happen to this equilibrium is going to shift to the right. What are we going to make? Conjugate weak base. Yes? Yeah. Or you could also show the reaction as CH3, COOH, plus NaOH goes to, and this is a one-way arrow, Na, CH3, COO, plus H2O. And if we are halfway through that neutralization, you will have some excess of this, and you will have made some of this. Yeah? Yeah. So this area right here is called the buffer region, because we have made a buffer solution by adding some strong base to the weak acid. That was that alternate method of making a buffer, if you recall. Yeah? Okay. So if you were asked, why is the pH at the equivalence point greater than 7? In this particular example, where we have, so this is our equivalence point. This is all gone. Our acid is all gone. Our base is all gone. So the only species present at the equivalence point are the salt and water. So we're going to focus on the salt. Which half of the salt do we care about? The acetate. Okay, so what is the pH at the equivalence point? It is about, what, 8.3? Okay, let's call it 8.3. Who is the salt? NaCH3CO. Who are the ions? Na plus, CH3COO minus. Do they hydrolyze? Does Na hydrolyze? No. Does CH3COO minus hydrolyze? Yes. Write the hydrolysis reaction, if any. Is this solution acidic, basic, or neutral? Basic. Would you be able to calculate the pH if you had to? Probably. You'd have to do some math, right? You'd have to be like, okay, how many moles of the product did I end up? What's my total volume? And then you'd have to do a rice table. It would be a pain in the ass, but you could do it, okay? All right. After the equivalence point, it's just the excess base. We've already talked about that. And this just shows weak acid versus strong base right beside strong acid with strong base. And you can see that the curves become the same after the equivalence point. So for our weak acid, weak strong base, you are going to look for higher initial pH. Can I just call it pHi? You are going to look for the hill at the beginning, hill at the start. And you're going to look for equivalence point, pH greater than 7. So those are your 3 clues. Yes? And do you notice what's happening with our pH just before this point here? It's going up faster, yes? That's because we've not yet hit our buffer region. Okay? So this little segment in here, I remember when I was in high school, I was like, buffer region. I thought it was just some magic thing because we never got an explanation of it, really. Like, I don't know why it's a buffer region. Oh. And it was funny because I'd look at it and I'd be like, the pH is changing faster than in a strong acid, strong base when there's no buffering. So that made no sense to me whatsoever. But it just means that once you hit that buffer, it'll change slower than if you just kept getting rid of the product. I don't know. Just ignore me. There we go. All right. The acetic acid, if the acetic acid being titrated here were replaced by hydrochloric acid, what would happen to the amount of base needed to reach the equivalence point? So this graph is we are adding NaOH to acetic acid, CH3COOH. What would happen to the volume to get to the equivalence point? If we replaced CH3COOH with if we replace the acetic acid with HCl. So if we replaced the weak acid with a strong acid. Right now, it takes 50 milliliters. We're going to keep the concentration the same. Have a little chat about that with your neighbor. Sally, I want to go bowling on your desk. I love it. What do you guys think? Is it going to increase the volume needed? Is it going to decrease? Or is it going to stay the same? Or I don't know. So you can be like, volume will increase, volume needed will increase. If we replace the weak acid with the strong acid, volume will decrease, volume of NaOH will decrease, or volume will stay the same, or I don't know. I've got a decrease, I got an increase, I got some stay the same, and I got people who are not voting anything. It's okay to vote I don't know. So you should not, okay, everybody needs to move their arms in some fashion to show me what there is in their brain right now. Because I cannot read your mind, and it's okay not to know. No, you need to like show me. Like this, I can't, can you see what I'm doing with my hand? I cannot see this, right? Like as far as I know, you're not doing anything. Okay, Hannah, why are you doing nothing? This is not an option. You get to vote up, down, stay the same, or I don't know. That's fair. Lots of I don't knows, lots of ups. Any stay the sames? I gotta stay the same. Gotta stay the same. Okay. Let's think about this. I'm just going to call it HA because I don't want to write out all of acetic acid. And let's see, this was 50 milliliters of 0.1 molar. So how many moles is that? 5 millimoles. Okay. Our hydrochloric acid, HCl, plus NaOH goes to Na plus, oh, hang on. Yes, okay. H2O. And again, this is 50 milliliters, right? Because we didn't change the volume, we didn't change the molarity, we just changed the substance. So we still have 5 millimoles. And the NaOH, the concentration is still the same. We have 0.1 molar. In order for neutralization to be complete, how many millimoles do we need? We need 5 millimoles, yes? How many millimoles do we need of the NaOH to neutralize the HCl? Also 5. And we know that we used 50 milliliters. And so this would also have to be 50 milliliters. So does it change the volume? No. Okay, and that's because regardless of whether you have a weak acid or a strong acid, that reaction is pushed to completion by the strong base. And so it's really only the moles that matter to get to the equivalence point. Yes? Only moles matter to get to the equivalence point. So no, it doesn't change the volume at all. Okay? Because the moles of acid needing neutralizing is the same. I'll be with you in just a second. I'm going to write this down first. You had a question, Justin? If it was a weak base and a weak acid, you cannot have complete neutralization because they'll just hang out in an equilibrium with each other. They won't go to completion and you'll be like, okay, well, that was pointless. Oh my God, what am I doing? How did that happen? Drinking problem, apparently. Gracious. Okay. All right. So this just gives you pictures of what's happening there. I guess the bell's going to go in like any second, right? So you guys can do page 87 and study for your quiz. That is 5.3, 5.4 A and B. No 5.4 C, because that's more like titration curve kind of stuff.
What section do we go on to?
Which what? Who?
Like this Tuesday.
Yes. Oh, this Tuesday. Let's check. Because I don't remember. Okay, let's stop recording for starters here.